This is your telescope, an engineering marvel, an exploration powerhouse. Use it to look back in time and explore the first galaxies that formed after the Big Bang. To peer into atmospheres of planets orbiting the stars. It's your eyepiece to the uncharted, unknown, and unimagined. This is the largest, most complex, and challenging space telescope ever constructed. It will change our understanding of the universe and our place in it. The James Webb Space Telescope.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Well, hello and welcome to the Global Classroom, a unique and inspiring initiative that connects children and educators all over the world. Working with our global partners and special guests, we aim to be a beacon of hope and inspiration that unites and empowers children all across the globe. Now, wherever you're tuning in from right now, wherever you're on the world at all, don't forget you do have the subtitles box at the bottom down here, and our Q&A section is open at the top of the screen as well for any questions that come in also throughout the classroom. My name is Jeff Shaw. I'm the headmaster of Scarisbrick Hall School. I'm delighted to be your host today as we stream live from the wonderful and impressive Oak Room here at Scarisbrick Hall, the home of the Global Classroom. Now, in today's episode, we are asking all of you just to stop, to look upwards and to think about the wonders of space as we learn about the incredible James Webb Telescope. And our guide on this journey of discovery is the James Webb Telescope Deputy Project Scientist for Planetary Science, Dr. Stephanie Milam. Now let's take ourselves across there right now and make sure we can hear us. So Stephanie, welcome to the Global Classroom. First of all, can you hear me and how are you?
I can hear you loud and clear and I'm wonderful. Thank you so much for having me.
So where are you coming from today? Where are you beaming in from today in the world?
I am coming from a beautiful Maryland in the United States, just outside of Washington, D.C.
And what's the weather like today outside? It's quite early for you in the morning, but
it's a nice, clear, sunny day, actually. I'm going to have to go outside after this.
Sounds absolutely wonderful. It's a privilege to have you here today and what you're doing, and it's great to talk to you. And I've got to say, there's quite a lot of excitement about what we're going to talk about, a lot of interest. We've had messages sent in from all across the world. People asking about you and your journey, inspiring people, and messages all about, what is this wonderful thing in space? Is it going to work? How's it going to happen? What's going to reveal to us too? Before we get on to what you're working on right now in the project, would you mind explaining to everybody who's watching and listening today what you do and what it actually entails?
Sure. Let me show a little bit about what I do. So I put together a little montage for you to describe a little bit about what it is that I do. So I am a scientist at NASA Goddard Space Flight Center. I not only work on the James Webb Space Telescope as the deputy project scientist for planetary science, but I also have a research laboratory and I use telescopes all over the world to study objects in our own solar system. So my role on the James Webb Space Telescope, though, actually was not as an engineer or a technician. I am representing the science community, and actually by that I mean the solar system science community. We have this huge space telescope that's supposed to, look at the first stars and galaxies across the universe, but we wanted to make sure that we could actually study objects a lot closer to home, so things like Mars or Jupiter. And they brought me on to help out on this part of the project to make sure that we could actually do that kind of science.
Wow. So you say, it's an interesting side, not being perhaps on the engineering side of it, but it sounds like a fascinating project, an exciting project, and one I'm sure that you've been very blessed to be a part of as well in your life. And out of our questions, perhaps you want to start now and sort of say about your own personal journey, okay, and how you got to this point and how we got there. So let's unpack a bit about your life as well. And I'd like to start, if I can do, with a question that came in from Nepal. Wonderful place to go and visit in the Himalaya side of it, and a beautiful country as well. I know we've had probably a few connections on sound getting through to Nepal before, but let's try and connect to Nepal right now. And I've got a question coming in from Shaolin, who's actually only 11 years old, but is somebody who's quite inspiring as well. So I think from my point of view, if we can hear Shaolin say the question, I can't quite hear her right now. Let's try and get her through in a second, okay? So we can get it through. And she's actually only 11 years old, and she's somebody who's got a question for you about what you're saying. So let's try and hear Shaolin right now. I could see her a second ago, and let's try and hear what she's saying and what she wants to say about inspiration. I presume it's about her own view and what she might want to do potentially in her life going forward. So let's try and get across now to Nepal if we can do, and hear a question.
My name is Saulin Maharjan. I come from Nepal Anujati boarding school. I am 11 years old and I study in grade 7. What is it that gave you an inspiration to become a scientist and work with NASA?
Okay, well, I heard that definitely loud and clear. Definitely some with high aspirations there. Very young right now, but Stephanie, what's the advice then?
So what gave me the inspiration to become a scientist to work at NASA was absolutely visiting a NASA Space Center when I was a little girl. At around the age of 6 years old, I had a school field trip that actually took me down to NASA's Johnson Space Center. This is in Houston, Texas. A lot of people are familiar with it. That's where they have the mission control for the astronauts. And we got to go on a tour there. So I grew up in Texas and I came home absolutely ecstatic and told my mom one day I was going to work for NASA. I grew up around airplanes and watching the space shuttle going on all of its journeys. I got to watch, the Hubble Space Telescope get launched. All these things had huge impacts on my life and my career and absolutely influenced why I wanted to work for NASA.
Brilliant. So I guess even now NASA's doing things like the James Webb, like I guess Artemis is going to be going through. And I think you mentioned coming from Texas over there. I know some people would probably say Texas are very famous for their food as well and barbecue. Is that something you enjoy in Texas as well?
Absolutely.
Yeah.
You have to have barbecue if you're a Texan.
I hear a lot about that certainly as well. Fantastic stuff as well. So, okay, so that's your inspiration that you receive seeing things going on, which is amazing to hear about that. And there are some great things. I'm sure people watching today will watch this idea about the James Webb and hopefully be inspired as well. But there are some more precise questions going on there about somebody who's perhaps, we've got a question I think from Uganda we're going to go to now, which relates more to do perhaps, there's somebody who's going to be a budding future scientist. They're perhaps in school right now. So let's try and hear if we can do from Uganda. I've got somebody who's age 9 called Michelle, and she's quite inspirational and she's full of energy on here. And let's see if the sound comes through from Uganda and have this question in now. Well, I can see somebody, but I can't hear them right now. So I'll ask the technical team behind the scenes to try and get the audio on that side. If you definitely want to hear her, she sounds fantastic. Wonderful. Well, I can see her, but I couldn't quite hear her. So I'm going to go 5 more seconds to go back to Uganda so you can hear on that side of it, because I really want to hear what she's saying about the future and her own views as well. So let's try connection one more time to Uganda.
Hello everyone, my name is Michelle Ayagil. I'm from Uganda. I'm 9 years old and I'm in primary 3. And my question to Dr. Stephanie is, if I want to become a scientist, what should I learn in school today? Thank you.
Wonderful, exciting there on the side of it. So Stephanie, what would you say to that then?
So I think the best thing to do as far as studies go and pursuing a degree in science and maybe someday becoming a scientist and working for something like NASA is to do all the science classes you possibly can. It's not about being an astronomer. It's not about being a physicist. It's all about knowing all the different types of science, how to learn and study and enhance the things that you already know in different ways. I also encourage students to take all the math classes they possibly can, but those aren't the only things that we need as scientists. We actually have to know our history. We have to understand where all the key questions that we're trying to answer today, where they came from, how scientists before us actually worked on those problems. So really getting into the history and the details and the background of the information that we're trying to study today. We also have to be writers. We write and present our science so that our other scientists in the field understand what we're doing and they know the process and the key steps that we had to take to answer some questions. And finally, we have to be able to be speakers. We have to be able to portray our knowledge to everybody else in the world, including students like you all. So it's all about just being a good learner and applying what you can learn in different ways and different techniques.
Really interesting. So I think it's almost saying that science has to have a complete package right now, be able to present things and ideas. And even what you're doing today as a scientist is talking to young people, putting it across in the right kind of way as well. So encouraging all the sciences, keep presenting, be confident, and take every opportunity to share things and to connect as well at the same point in time. That's really, really helpful as well. So from your point of view then, could you talk us a bit about your journey from when you went from the idea of going through school, what you did and how you studied it yourself and went from there perhaps?
Absolutely. So a little bit about how I pursued my career. I actually wanted to be an astronaut. And so I was taking all of my math and science classes up until the point that I found out that I wasn't actually tall enough to be a pilot for the space shuttle.
Oh, no.
At that point, my whole career path changed from being a pilot to now being an actual research scientist, because the only other way to be an astronaut when I was in school was to be what they call a mission specialist. And so that's somebody that works on the space station, running the experiments, or the astronauts that are walking around on the moon, collecting moon rocks, or doing experiments in microgravity. And so what I did, I decided to pursue an education and a career path that would give me the most tools in hand and resources and education that would make me the best type of application scientist or mission scientist. And so I followed a degree in chemistry. That way I knew how to run experiments, I knew how to troubleshoot experiments in different conditions, and I had a lot of experience working in different types of areas. So everything from, studying what the composition or contaminants are in groundwater or in dirt or soil samples, to seeing if there's lead in paint samples from various buildings, but also doing things like studying chemistry of unique molecules, analyzing meteorites. All these kinds of things gave me like that hands-on tools that I really needed if I were to go to space and be able to conduct experiments.
And we noticed, of course, in your qualifications, you've got a doctor in front of your name as well, which is interesting. And that, from our point of view, relates to a research you've done, an in-depth research. And I think one of the questions that we had that came in was from a student aged 12 called Eddie, who had a particular question about that element as well. Let's keep our fingers crossed that we can hear Eddie right now. And let's try and log him into the classroom and hear what he had to say.
Hi, I'm Eddie Krug. I'm in year 7. How long did it take you to do your PhD or doctorate?
Okay, Stephanie, this one over to you. So how long does it take to achieve that as well?
So in the US, it's a little bit different than other education systems around the world. I got my first degree, which was a bachelor's of science, in about 3 years, which was a little fast compared to a lot of my peers, but that was because I took a lot of coursework when I was in high school, and I took a lot of classes at night and over the summer semesters to try to make my education go a little bit faster. In the US, if you have a bachelor's degree in science, you can immediately get into a lot of PhD programs without having to go through a master's degree. That makes our PhD programs a little bit longer than what you would have if you were, for example, in Europe. And so our PhD programs are typically for something in the physical sciences, about 5 years. And it took me just about 5 to get my PhD without having a master's degree first.
Wow, that's quite a long time and a big commitment, but obviously worthwhile to make it where you are right now and to achieve equally as well. You talked about your journey through your qualifications and your achievement as well. We had a question that came from Italy as well, which talked about, are there any challenges that you faced in becoming what they called a lead scientist where you are right now, obviously top of your field? On that journey you went on to, were there any real sort of challenges or hurdles that you faced, and how did you overcome those?
I actually had a number of challenges. One, I'm not very good at standardized exams, and so I had a lot of challenges learning how to get through all of those for, I don't know, getting through my everything from high school exams through my undergraduate to tests that we had to take just to get into college and tests that you had to take to get into graduate school. And so those were usually the hardest things for me to overcome. But I also had other challenges, including things like I'm a woman that was working in astronomy, and there aren't as many female peers, especially senior scientists or mentors that were supportive of women. And so that was a barrier that was a little bit challenging at first, but things are definitely getting better. Even in my career, I don't think I want to call it a short career anymore. I'm feeling very old today. But I have seen the improvement and the support that's going around, encouraging not only women in astronomy and physics, but also minorities or underrepresented people across the world. And I think for the next generation, it's definitely going to be a far better place for all kinds.
I think it's really interesting that you raised that as well. And I think being here, being on this classroom, talking to the world about being, a scientist in what you're doing, being a woman in that situation, and saying actually it was tough first of all, but now it's getting into a more positive light. We're very encouraging here at that side of it. I want to make sure it's right, and we know there's going to be some young girls, some young women out here watching this, asking questions from, I don't know, example in Uganda, who's asking, how do I do this? And we're saying actually you can go ahead and do it. We don't. And I think your message there is a very, very positive one, that we're seeing a shift in that culture right now, and you're part of that. So thank you very much for driving that through on behalf of everyone watching this program. Myself, I think it's exceptionally important about equality as well. I have my own children who are girls as well, and I want to make sure they have every opportunity in their lives. And so thank you for being a pioneer in that as well from myself equally. We talked about yourself for quite a bit. Let's get on to something really exciting. I can see it in your background as well. Let's talk about this amazing telescope that's up there. Well, it's inspirational to hear about your journey and what you've achieved. And there's no doubt that if we go around the world right now, we can see that people are incredibly interested in the James Webb Telescope mission. And putting it into perspective, it's perhaps a really powerful example of positive global collaboration, because although you're over there in the US, we're broadcasting from the UK. We've got people around the world, in Asia, Nepal, Uganda, Europe, watching this, in Africa as well. But we know this project was a global collaboration, and in fact, throughout a time when it was a really challenging time for many of us on the planet in the last few years, particularly. But let's take a quick question first of all, and perhaps try and unpack this incredible step that we will hope transform the way that we see our universe. So I'm very positive about it. But let's see, a question now from somebody who's a bit younger. Let's get a question from Pranay, if we can do as well, and see what they have to say for the classroom.
Hi, I'm Pranay Ravardi and I'm in Year 7. What are the main scientific goals for the James Webb Telescope?
Great question. Okay, Stephanie, you ready for that one?
Absolutely. This is one of my favorite questions, and as a scientist, one of the best things that I get to actually talk about for this project. So let me, please indulge me for a moment, because this is going to take a little bit to get through. The science capabilities of the James Webb Space Telescope actually were inspired by the Hubble Space Telescope, but we wanted to make sure that this observatory was fully capable to observe everything. We wanted it to be just as successful as the Hubble Space Telescope was, observing things from distant galaxies and stars to planets around other stars in the universe, as well as studying things in our own solar system. So our science goals for the James Webb Space Telescope actually were inspired by the Hubble not only for the motivation of building a large infrared telescope, but also making sure that we had capabilities that covered the entire astronomical, astrophysical, and planetary science communities. So I'm going to start with the Hubble Ultra Deep Field. This was the inspiration for the James Webb Space Telescope. What we discovered with the Hubble Space Telescope was that we could see things much further and much clearer than we ever could have imagined. The capability of this telescope to stare deep into space at a speck of the sky. I mean, if you were to project the Hubble Ultra Deep Field onto the sky, it's about the size of your fingernail if you were to hold it up in the sky. And what we saw in that fingernail image of the sky was tens of thousands of galaxies. And so this video is showing you sort of stepping through as we go from our universe that's near us all the way back to as far as we could see in time with the Hubble Space Telescope. You can see that we start getting further and further away. There's less and less galaxies. Things aren't nearly as pretty and structured as they were in the beginning. And all of a sudden, everything stops. We reach a limit that we possibly can't breach with the Hubble Space Telescope. So in order to look further back in time or deeper into space, we had to have something that operated at longer wavelengths. And this is because the universe is expanding and things that are moving away from us, the light actually gets shifted to longer wavelengths. So we needed a really sensitive telescope, as sensitive as the Hubble Space Telescope, but something that operated at infrared wavelengths. And so that's how the James Webb Space Telescope was born. And so some of the key science goals are absolutely to study and push into this realm of how far back in time we could actually see with the James Webb Space Telescope. And so our primary science goal is to study this evolution of galaxies. How were the first stars and galaxies actually formed? How do galaxies and stars actually evolve through time? By having access to seeing all the way back into the early galaxies of our universe, we can see how things actually started to form, how they started to actually become these beautiful spiral images that we can see of galaxies in our nearby universe. We could see how they start evolving, whether or not they completely annihilate themselves, if they merge with other galaxies, and how things actually form and evolve within them. Also at the infrared wavelengths, these longer wavelengths of light, we can actually start peering into clouds. So just as we have clouds in our own sky that block out stars or block out the sun, there's clouds all over our galaxy. And this is where stars and planets are actually born. With these wavelengths that the James Webb Space Telescope operates in, we can actually see inside of those clouds, like with night vision goggles or X-ray goggles. We can see inside of them and see how stars are actually being formed and planets are actually being formed. So what you're seeing in this video is actually a Hubble Space Telescope image of one of these giant clouds in space where stars are being born. Hubble operates at the same wavelengths that our eyes can see with. So this is visible or optical light. So once you go to further and further wavelengths into the infrared, you can see that now our night vision goggles turn on and we can see inside of these clouds. So this is going to be a whole new area of science and discovery with the James Webb Space Telescope. Also, we can study planets around other stars. The way we do this is we watch a star, and whenever the starlight actually dims, that's because there's a planet, most likely, passing in front of it. And how much it dims depends on how big that planet is, how frequently that planet orbits its star, and whether or not it has an atmosphere or not. Whenever these planets go in front of their star, we have that opportunity to not only study how big they are, how often they orbit their star, but also understand what the composition of that atmosphere may look like. So this is something called transit spectroscopy. So what we're doing is we're actually looking at the tiny little bit of atmosphere or puff just above the solid surface of a planetary body, and we can see what the gases are within that atmosphere. So this is what we call a spectrum. So this is where we're looking for the fingerprints of given molecules in an atmosphere to understand what that atmosphere may or may not be comprised of. And so this is an example of what the Earth's atmosphere would look like if we were studying it with this technique. And we have lots of things in our atmosphere, mostly nitrogen, but we also have things like water and carbon dioxide or methane gases. And so by looking for these individual molecules, we can understand what's going on in that planetary environment. And this is something that we're going to be doing with the James Webb Space Telescope. Finally, we're going to be studying objects in our own solar system. I'm just going to touch on this briefly because this is what I get to do for a living. We have a funny shaped telescope, so we can't actually look at the inner solar system because that would make our telescope way too hot. So we look at pretty much everything from Mars on outward, but this includes things like Mars, asteroids, Jupiter, Saturn, etc. And this is going to be a very exciting area of the science that we actually get to do with the James Webb Space Telescope.
Wow, I think that's a huge amount of stuff to deal with and to work through, isn't it? It's extraordinary what can be achieved. And I think from a simple question there, what are the main scientific goals? We've gone with this sort of huge explosion of ideas behind that. Right, so when we first talked about launching this classroom, we had a lot of questions coming in, and a lot of them were the same actually. So, and they evolved around kind of what might happen with the telescope and once it's been launched and issues about that. So we had a first question about, you know, how the telescope was made, how did it happen? And then, you know, what happens if something goes wrong or breaks on the telescope, because it's not like going down to a store and getting it fixed. There's no care plan for it. What happens if the telescope doesn't unfold correctly? You launch it and then suddenly this incredible thing you created doesn't actually assemble correctly in space. Even a question about how do we stop bacteria getting on the telescope? So, Stephanie, can you sort of walk us through that kind of questions there and how we actually got this tremendous thing out there and operational? Is that possible?
Absolutely. All right, let's get into the details of the James Webb Space Telescope. All right, well, first and foremost, this is a huge telescope. Launching something that's this big is an achievement that we hadn't ever accomplished before for a space science telescope, either with NASA, the European Space Agency, the Japanese Space Agency, or you name it, pick your favorite space agency. Having a scientific telescope this large was a challenge of engineering in and of itself, and we were able to accomplish this through many different feats. First, I want to just give you a little bit of perspective of how big this telescope is. So the James Webb Space Telescope is actually 6.5 meters as far as the diameter of this large gold hexagon mirror goes. Now, compared to the Hubble Space Telescope, that mirror was only 2.4 meters. But even being as big as it is, so you can see it's an enormous, it's the size of a small building compared to about a school bus or a tractor trailer type size of the Hubble Space Telescope. It's almost half the mass of the Hubble Space Telescope. So that means that we had to make something this big weigh only half as much as what the Hubble Space Telescope was when we launched it. This is because we were launching to a much further distance from Earth than the Hubble Space Telescope is. And we also had to have something much, much bigger. So going that far, having the rocket fuel to get us to where we're going, and to be able to launch something this large was something that we had to take into consideration. So one of the innovations that we did was we actually have lightweight mirrors. So we have a giant hexagon for a mirror that's 6.5 meters in diameter, but that's actually made of individual mirrors. So 18 individual mirrors. And these mirrors are actually made out of beryllium. And if it was a solid piece of beryllium for each one of these mirrors, they would be about 550 pounds or 250 kilograms each. But what we did was we lightweighted them. So we basically honeycombed them out. And we made them go from 250 kilograms all the way down to only 20 kilograms. So extreme lightweighting. And that's done by basically hollowing out the solid surface. And you can see that in this picture here, how it's sort of bored out, where each of these tiny little ribs that are supporting the structure, the honeycomb part of the structure, is about 1 millimeter thick. We also have controls on the back of each of these mirrors, which helps us control and make sure that all 18 segments actually act like one solid mirror. Another thing we had to do was we had to protect our telescope. The Hubble Space Telescope's in this nice protective tube, which is why you don't actually see the mirror from the outside. The James Webb Space Telescope, we sit sort of like on a boat. And so we had to actually shade our primary mirror. And we did that the same way a sun umbrella or beach umbrella works. And this gives us basically an SPF, or sunscreen, of about 1 million. So just by putting this telescope in the shade, we can cool it down from 85 degrees on the hot side of the telescope, so the bottom side of that sun shield, down to a mere negative 233 degrees Celsius on the cold side where the mirror is. So this was quite a challenge in and of itself, because to have a sunshade that's big enough to protect that big 6.5 meter mirror, we had to have a shade that was about the size of a tennis court. So this was something else that we had to be able to fit and fold and put inside of a rocket. So the next challenge we had was, how do you put something that large into the fairing of a rocket? So this was a whole game of origami in and of itself, folding a telescope to make it fit into a single fairing of a rocket. So what we did was we actually have deployments now, so we can fold our mirrors, which is convenient since they're segmented. And then we have the sun shield that we actually are able to sort of crunch up and then fold so that everything fits nice and tight into the fairing of a rocket. And this is what it looks like in its launch configuration. So there we are. Well, that's me sitting there with the James Webb Space Telescope just before it went down to French Guiana for launch last fall. But to fold this giant sun shield was also a challenge, because in space, we're not fighting with gravity the way we are here on Earth. So figuring out how to test all of these mechanisms was something that was quite a challenge in and of itself as well. Part of the questions that I was asked was, what if something didn't actually work? Well, the good news is every one of the mechanisms that deployed this telescope had what we call redundancy, or a backup. We also have sensors going all over the telescopes and every one of these parts that move, telling us whether or not that part successfully deployed or not. And if it didn't, we could either try it again, or we could use the backup if there was a backup mechanism. Everything was controlled from ground, so we knew exactly what was happening at any given time, and we were able to troubleshoot things in real time should they have actually happened. The good news is everything worked beautifully, and we didn't have to worry about any of those types of challenges. And so we now have a fully deployed telescope in space.
Awesome. Thank you for sharing that. I mean, I've got to say, from my point of view, that picture with you on the launch pad it's a whole sort of the gravity of the whole thing, and the size of it is enormous. I mean, I think from my point of view, just packing it down and the whole concept of getting it done. When you're actually launching it, Stephanie, when it went up there, was a kind of nervous moment of each one being successful and ticking through, done, completed, done, completed? Oh, how scary is that?
It was terrifying. Actually, I'm gonna share one more picture with you, just to emphasize the gravity of the situation. So this was our whole deployment sequence. So we launched from Earth, and within a matter of moments, we had 2 deployments that actually happened automatically. One was our solar panel. So in order to get power to the telescope, we had a solar panel that automatically deployed. We actually even saw this in the cameras from the rocket itself after we launched, happening right at the end of before we lost all imagery or real-time imagery of the spacecraft. So that was really exciting. The second automatic deployment is our communications. So we have a small little communication satellite that pops out of the bottom of the telescope as well. And that's so that we could control all the other deployments. So what you're seeing here is our full deployment sequence. So this is it, as we launched it in that folded up picture that you saw me standing in front of it. And so we went through a whole series of events of unfolding the sun shield, which took weeks, all the way down to actually now unfolding the mirrors of the telescope. This whole sequence actually happened on our journey to get 1 million miles away from Earth. and are 1.5 million kilometers away from Earth. And it took us an entire month to unfold this telescope. And I can tell you, it was a month of terror. All of us were sitting there anxiously awaiting what the next deployment was, reading the telemetry, making sure all of our sensors were giving us all the right signals, and making sure everything worked flawlessly. I will say after that month, I slept a lot better.
I bet.
But yeah, so that it was definitely an intense period of time, but everything, as I said, worked amazing, and we are into the final phases of commissioning our telescope.
It's incredibly exciting to hear, and I guess all relieved that all the money and investment, the scientists, the huge team can now not quite breathe a sigh of relief, but get on to that next stage and getting some data beyond that as well. Interesting question came through from South Africa as well in a second. I think we're moving now to about our thinking about what might come from the telescope and go beyond there. So let's hear a question now from South Africa, if we can do possibly.
Hi, my name is Lindy Longobese, news editor at MUT Campus radio station in KwaZulu-Natal, Durban, South Africa. My question for you today is, how do you think the James Webb Telescope will change life beyond our planet? Thank you.
Okay, interesting question, and we had a lot of interesting questions about this and what's going to happen, and their understanding of what's going to happen from there, and our understanding of life beyond this planet. So what's your take on that, Stephanie?
So understanding of life beyond our planet, that's always a fun question. And I think it's something that we're going to start just scratching the surface of with the James Webb Space Telescope. So we don't have the goal of actually finding life itself. What we're actually going to be doing is we're going to be studying different environments and seeing whether or not there's something that gives us a clue to some process happening. So be it, let's think of a planet around another star, and we're looking for something that looks like Earth 2.0. So what we're going to be doing is studying the atmosphere of these planets, and we're hoping to look and find something that looks a lot like the Earth's atmosphere. But there may be other ways that life could exist. Look at the extreme circumstances of all the atmospheres, even within our own solar system. We think that there might be places that life could actually exist within our own solar system in these very extreme environments. So the thing that we're actually looking for is something peculiar occurring within these objects. So think about all the processes that can make a planet look peculiar. And this goes all the way back into the early Earth. When we had a heavy bombardment era, there's all kinds of dust being spewed and crazy things happening to our atmosphere, losing all the water on the planet. These are kinds of things that are suggesting that there's a unique process happening. Volcanoes, every time a volcano erupts, we have this huge plume of gas and dust. So seeing these kinds of things suggests that we have an active planetary body. And those are the kinds of environments that might be really, really interesting to do some follow-up studies, maybe with the next generation of space telescopes. Who knows? These are the objects that we'll be following more and more closely if there are these peculiarities. And so not only in planets around other stars, but even within our own solar system, we're going to be looking for these types of clues. And so that's really, I think, what's going to be the impact. And I think the James Webb Space Telescope is really going to help us get that initial amount of information on key objects that we should really do follow-up studies and do further, observations to see if there's something like life there.
So in some ways, it may pose more questions to ask to go beyond here, and some different ideas as well from that telescope findings, which I think is quite interesting. Now, a beautiful country, Ireland, not too far from where we are now, I guess, across the water. And we had a question coming in from a pupil in the classroom who's age 10, Ranul as well. And I think we can connect to Ireland right now and hear that question he wants to ask.
Hello, my name is Renewal Degnan. I am 10 years old and I am from Castleburg School, Dublin, Ireland. My question for Dr. Stephanie Millen is, what would you do if you found living forms, and would it contradict others' beliefs?
Okay, wow. I say for a young man, age 10, that's quite a deep question and beautifully read and a wonderful accent as well from Ireland. So it's definitely an interesting one, that one, to throw in that. I guess people are thinking about it. What are your thoughts around that?
So I think that is the absolute question of, is there life out there? Humanity has been trying to answer this question, as long as we've been around. And this is the ultimate goal, is figuring out, how did we get here? Are we alone? Is there potential for life or another planet that maybe we could survive on? So I don't think it would have an impact on people's beliefs just beyond, oh wow, we were right all along when we finally found it. But I do think it's going to have what finding evidence of living forms would actually do for humanity is give us that sense of possibility, that there are other life forms. And if we ever discover something like life, which we're not expecting to do with the James Webb Space Telescope, but maybe we have a mission that's going to the Europa, the moon of Jupiter. So it has this huge ocean underneath of it, and we believe that there's enough energy under that ocean that could actually help sustain life. If we send this mission there sometime in the next decade or so, and we find evidence of life, or we even find, let's say, bacteria there, that's huge for us. That means that we can actually start investigating how life exists in other extreme environments. And it also tells us that we're not alone. Maybe it starts giving us some evidence of how we actually got here. Was it just a ubiquitous chemistry that was, there when the solar system formed and the planets formed? Was it, the right ingredients were delivered to an early Earth at the right time in the right conditions? Or maybe it was something that we don't have the answers to, or we don't even have the questions to answer yet. And so just by the discovery and the realm of what we may or may not find gives us all the information and all the clues that we need for further exploration. And I think that's the key goal as scientists, as astrobiologists. We want to know how things came to be and or how they could possibly exist in other environments. And so the more evidence we gain, either positive or negative as far as supporting life, or evidence of past life, or potential areas or environments that we could actually have as a habitable world, all of that information comes into play. We do models, we do laboratory experiments trying to simulate these environments and understand what these conditions actually are and what it means for life itself.
Brilliant. Well, thank you for the answer on that side of it. I think from my point of view, it's almost the descriptions about this is a great telescope out there that's almost like a ship sailing in space when you see it visually, but has a sense of going out there with great exploration behind it to create questions, to generate questions, to provoke thought. And it's quite a powerful message when you talk about it in that kind of way. Just while we are on the live chat, and I know time is ticking by, but we're actually on track very well on our time schedule here. There's a couple of questions that are coming in that are consistent to be asked as well, and I said I would raise these on this side of it. So one question is quite straightforward. It's asking about your sort of day-to-day job in the role that you do with the telescope, and quite a few people are asking, saying, well, actually, what is it like, and what do you actually do day to day? And so, if there is such a thing, Stephanie, as a normal day for you, what is it like?
I don't know that I have any one normal day ever in my entire life. Right now, as we are commissioning the James Webb Space Telescope, what my life is like is sitting anxiously at a console in the operations center, waiting for data to come in as we're slowly in the process, our final process, our phase of commissioning our telescope. And so what that means is we've perfectly aligned every instrument and every part of the optics of our telescope, and it's amazing. And actually, I have to share with you some of our latest images just so you can understand how exciting it is.
So how recent are these images? They're quite recent ones, or are they?
These were ones that were released actually 2 days ago.
Wow, fantastic.
So let's show you some of this. All right, so what you're seeing is actually our final image that we verified that the telescope and the instruments were fully aligned. So we went through this long, arduous process of making sure all of those 18 segments of the primary mirror were properly aligned. And then what we had to do was align each one of our science instruments, which there's 4 of them. So there's the near-infrared spectrometer, the near-infrared camera. These 3 on the bottom are actually a unified system. One is actually so that we can point our telescope, and the other one is another instrument called the nearest. And then we have our mid-infrared instrument. So what you can see is all these beautiful stars. This is actually looking at a pretty dense field. And what we did most recently is we looked at one of our nearest galaxies, and we stared into it in the mid-infrared with our mid-infrared instrument. And this is a comparison of what our previous state-of-the-art space-based infrared telescope could do, which is on the left. It's called the Spitzer Space Telescope. And at almost the exact same wavelength of what we were able to do within moments, just a blink of an eye, with the mid-infrared instrument on the James Webb Space Telescope. You can see the precision and the accuracy and the mind-blowing detail that we have portrayed in just these first images. This is my day-to-day life right now. I get to see these things popping in and sit there with my jaw hung open and my eyes bulging in sheer amazement of the amazing capability of this observatory. Every part of commissioning that we're going to be doing from here on out is just making sure all the modes of our telescope and our instruments actually work properly so that we can do the science that's been planned for the first year, and also for the next generation of scientists to come on and come up with their own ideas of things that they want to study with this observatory. So it's a very exciting time right now. It is pretty slow. We're in our last sort of month and a half, 2 months of commissioning. We're at about 130 some odd days now. So we're right here in the middle of our science instrument commissioning, and we should have our first images released to the public sometime this summer. Yeah, it's definitely an exciting time, and I'm looking forward to everything that's happening on a day-to-day level.
It's amazing. So I think when you showed that picture up before, I got a sense of just how small I feel sat here on Earth seeing that, and then quite an inspiring sense of how beautiful it is out there and how much there is to see and to find out, and the complexity of it as well. It kind of blows your mind in terms of the vastness of it.
Absolutely. I mean, I just showed you a picture of a star field. That's not anything like nebulas or what we're going to see in our own solar system, or what exoplanets are actually going to be, the capability of imaging exoplanets, or even what the first galaxies of the universe are actually going to look like. And these are the kinds of things that we are going to revolutionize for astronomy, astrophysics, planetary science.
So you really can't help but get excited. It's kind of a buzz, and you know,
I know, I'm like hopping out of my.
It's really, really exciting. One final quick question that came through as well, which is probably an interesting one to ask you before we get towards the end of our show almost soon, which is, what do you hope to find in terms of when you go there? When you go in there and the data's coming download, you're staring at a nebula, what's going to happen? What do you? I might see this. What do you dare to dream to see on this?
I don't know that I can answer that. I think what I'm the most excited about are the things that we don't even know exist.
That's it, yeah.
What are we going to see? What are we actually going to see? You just saw the capability of what our previous generation of space telescope was able to do at its best. And what we got with just a simple blink of an eye with the James Webb Space Telescope, the amount of detail, the crazy amount of accuracy that we can get with this instrument is something that I think is going to reveal all kinds of new discoveries and exploration for the future.
Brilliant. Well, can I ask you one favour? Will you come back in the Global Classroom and share with us some of the findings that you get from the telescope in the future?
Absolutely, I would be more than happy to do so. I'm beyond excited myself. So.
And we know we've got people listening in different age groups, aspiring scientists, people that, in truth, I should mention before, we actually have a school in Ukraine tuning in as well today. And we do wish them all the best in a conflict zone here, but we're speaking to them right now and we're saying, okay, what's your message, Stephanie, to those young people watching this right now who could be involved in the future, and it could be, downloading this data. They could even be doing a job like yours in the future for NASA as they grow up. What's your message for them right now?
My message is, this is your telescope. I grew up with the Hubble Space Telescope and watching all of the discoveries and science that it wasn't even planned to do, that it was able to do in the mission lifetime. The James Webb Space Telescope is just launched. We expect to have a lifetime of science of at least 20 years. So even early students, the youngest students probably joining us today, you will have the opportunity to use this telescope and explore the universe in ways that we can't even imagine right now. And so that is my message. This is your telescope. This is the next Hubble telescope. We're rewriting the textbooks, and we're really dependent on the next generation of scientists to help us do so.
Okay, well, what a powerful message. So get on there, get studying your science, get presenting, get learning. Stay tuned to NASA's website. Stay linked into the globalclassroom.com as well. And we want to see some exciting stuff happening on there. I mean, the NASA website, especially James Webb's website, have a great amount of information on there to go and look at. And we will signpost that from our website as well. From myself here at Scarisbrick Hall, I'm feeling quite inspired and mind blown in truth what this telescope can actually do and what it might do. I've got to say a huge thank you to the team that you're working with, to Stephanie, and to yourself for being here as well. And to everyone who's tuned in and watched this, thank you so much for sharing about this. And we hope to see you again in the future, tuning into the Global Classroom, perhaps with Stephanie as well, other episodes from myself and from Stephanie as well. Thank you so much, and we will see you again soon in the Global Classroom. Thank you.